Have you ever wondered how your favorite app or website can feel so instantaneous, while the massive data centers that power it are also trying to save as much energy as possible? I mean, it seems like a paradox, right? You can have speed, or you can have efficiency, but can you really truly have both? Well, that is the invisible battle that's happening trillions of times a second inside all of our computers. Okay, let's dive right in.
So, here's our roadmap. We're going to start with the fundamental choice that every single system has to make. Then, we'll look at the real-world costs of that choice in two very different arenas, the giant data center and the world of high-speed networks. After that, we'll see how engineers are getting incredibly clever to get the best of both worlds, and finally, we'll wrap up with why this quiet little battle actually matters to every single one of us.
And its very heart, this is the dilemma for anyone designing a computer system. What do? Do you build something that's always on, always ready, burning energy, just waiting for something to happen? Or do you build a system that saves power but might introduce a tiny but totally critical delay when it's finally called into action? For decades, this has felt like an impossible choice, a fundamental trade-off that's just baked into the laws of computing.
All right, so let's get to the core of it. This choice really boils down to two very different strategies for how a system waits for something to happen, whether that's new data coming in from the network or just a click from a user.
And these two strategies are called polling and interrupts. And honestly, this analogy is the absolute best way to get it. Polling is like a kid in the backseat of a car, just constantly asking, "Are we there yet? Are we there yet? Are we there yet?" It is a nonstop, relentless loop of checking. Now, this method is incredibly fast, because the split second something arrives, you know about it. But the cost is huge. You are using 100% of your CPU cycles just asking that question over and over and over again. Interrupts, on the other hand, are like telling your friend, "Hey, just text me when you get here." You can go about your business, you can do other things, you can even take a nap to save energy, and you only spring in action when you get that notification. It's super, super efficient. But there's a delay, right? The time it takes for that text to send, to be delivered, and for you to wake up and actually read it, that small delay is the trade-off.
Okay, so let's see how this plays out in our first arena, the modern data center. We're talking about buildings packed with thousands upon thousands of servers that need to be ready to serve your requests in mere microseconds. And here, the cost of being always ready is measured in one thing: electricity.
Now, this number, this reveals kind of the dirty little secret of data centers. To guarantee that instant response time we all expect, servers are often kept at a really low average utilization, somewhere between just 5 and 20%. So what does that mean? It means for the vast majority of the time, these incredibly powerful machines are just sitting idle, waiting for work. They are constantly polling, asking, "Is there a request yet? Is there a request yet?"
And this quote from a Google research paper just nails the problem. A server running at 10% capacity doesn't use just 10% of its power. No way. It might be using 50% or even more. And that's because even when the main processor cores are idle, all the other stuff, the memory, the network cards, the caches, it's all still powered up and burning energy, just waiting.
So you might be thinking, why not just use interrupts and let the servers go to sleep? Well, this slide shows you the catch. Modern CPUs have different sleep levels, or C-states. You can think of it like a light nap versus a deep, deep sleep. A light nap, or a shallow idle state, is easy to wake up from, but you're still burning a fair bit of energy. To get those real energy savings, you need a deep sleep state. But look at that wake-up time, around 100 microseconds. For an app that needs to respond in, say, 30 microseconds, 100 is an eternity. It's a complete non-starter. So data centers are stuck, burning all that power in these light nap states just to avoid that massive latency penalty.
Okay, let's switch gears and move to our next arena. We're shifting our focus from the cost of energy to the cost of time. In the world of things like high-frequency trading or large-scale machine learning or supercomputing, we're not just fighting for microseconds anymore. We are in a flat-out race for nanoseconds.
The technology that really enables this incredible speed is called RDMA, which stands for Remote Direct Memory Access. And the name really says it all. It literally creates a direct channel between the memory of two different computers, completely cutting out the slow operating system that usually sits in the middle.
And this illustrates the difference perfectly. On the left, with normal networking, every single piece of data has to go down through the operating system on one machine and then back up through the OS on the other. Every single step adds overhead and delay. But on the right, with RDMA, you see this clean, direct line. It's like having a private highway for your data, which is why it's so unbelievably fast. But, of course, there's a catch.
To use RDMA efficiently when you have lots of different tasks running, you can't just dedicate a whole CPU core to polling for data. You've got to use interrupts. And when you do, you slam right into a problem that researchers have actually called the killer microseconds. This is the extra 6 to 10 microseconds of latency that gets added just from the process of sending an interrupt and waking up the right program.
This chart from the research paper really shows just how deadly those microseconds are. Look at the far left bar. A simple RDMA operation using polling takes just 1.6 microseconds. That is blazing fast. But if you use an interrupt to wake up a process, even on the very same processor core, the latency jumps to 5.7 microseconds. And if that process happens to be on a different part of the chip, it skyrockets to almost 12 microseconds. The interrupt itself is now multiple times slower than the entire data transfer was in the first place. So we have this huge energy problem in our data centers and a huge latency problem in high-speed networking, and they both come from this same fundamental choice. So the big question is, how do we fix it? Well, this is where engineers get really creative, designing hybrid systems that try to capture all the benefits of both polling and interrupts. A classic example of this is actually found right inside the Linux networking stack. The system starts out in an energy-saving interrupt mode, just waiting. The moment the very first data packet arrives, it triggers an interrupt. But, and here's the clever part, instead of just processing that one packet, the system immediately switches into high-speed polling mode. It then tears through the entire burst of packets that have likely arrived right behind the first one. Once the queue is empty, it just switches back to the efficient interrupt mode to save power. It's simple, but it is incredibly effective.
Now let's look at some really cutting-edge solutions. To solve that data center energy problem, researchers developed something called Agile PKC. They basically invented a whole new kind of smart sleep state. It provides big power savings, just like a deep sleep state, but, and this is critical, it has a wake-up time that is over 250 times faster. And the results are just stunning. It can cut a server's energy use by up to 41% with practically zero impact on performance. It's a deep sleep that's finally fast enough for the most demanding apps.
And to slay those killer microseconds in RDMA, we've got FastWake. This is a brilliant two-pronged attack. The first approach gets rid of interrupts completely. It uses a dedicated dispatcher thread that just polls and then uses a super fast handoff, a 0.3 microsecond context switch, to activate the right application. The second approach is all about making interrupts smarter. It dynamically makes sure that the interrupt signal is always sent to the exact core where the waiting thread is sleeping, guaranteeing it takes the fastest possible path to wake up. Together, these tricks can slash that extra interrupt latency by up to 80%.
So we've gone pretty deep here. We've talked about C-states, RDMA, some pretty advanced engineering. But why does any of this actually matter to you? Well, because this fundamental battle between speed and efficiency, it underpins the entire digital world that we all live in. The real key takeaway from all of this is that the solution isn't to declare polling or interrupts the winner. The future belongs to these clever, hybrid, adaptive systems. Systems that can be incredibly efficient when they're idle, but can instantly transform into high-performance machines the very moment they're needed. It's all about engineering a way to get the best of both worlds, not being forced to choose between.
So the next time you tap your phone and get an instant response, or a web page just loads in a flash, take a second to think about the unseen battle that just took place. That instantaneous feeling is the result of decades of engineering, all designed to walk this incredibly fine line between performance and power. It is a world built on this constant trade-off. And now you can ask yourself, what was the hidden cost in either energy or complexity of making that happen?